Good afternoon, everybody. As you know, you're here for the Aspen Center Physics Colloquium, and this week is going to be an astrophysics colloquium. But I'm sure Hsiao-Wen, who's our speaker, presented a talk that will be exciting for everybody. Okay, my name is Pepi Fabiano. I am an astrophysicist at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts. I'm also a member of the scientific board of the center here. It's my pleasure to introduce our speaker today, Hsiao-Wen Chen, who's a professor at the University of Chicago, and she's been there about 20 years, she tells me. Got a PhD from Stony Brook, and has a postdoctoral appointment with Carnegie, a Hubble Fellowship with MIT, and then she went to Chicago. Now, Hsiao-Wen's area of interest is to study the gaseous halos around galaxies, which is important also to understand the feedback of the active supermassive black hole, the center of galaxies, the interaction with the halos around. Hsiao-Wen has done a lot of work in this field, and lately she is, I think she's the initiator, the PI of a big program with Hubble to study the warm-hot circumgalactic medium. She's going to talk to us about that a bit. This program is called CUMS, which goes for Cosmic Ultraviolet Baryonic Survey. And I think she's a fan of baseball, and she named it after the baseball team of Chicago. Hsiao-Wen is an astrophysicist, researcher, a teacher, and she also does a part of community service. In particular, she's been, recently, she is a member of two big NASA committees, the COPAG and the APAC, that oversight and give community input to NASA for the Cosmic Origins program and also astrophysics as a whole. Okay, so it's time for Hsiao-Wen to talk, and welcome.
It's a pleasure to be here, as always. A wonderful environment, very interesting discussion. Still my first week here, so very eager to meet with everybody. Today, I'm happy to have the opportunity to share some of my own research that's ongoing at the University of Chicago, also within a broader collaboration that you're going to hear about. And Pepe mentioned the Cubs team. I grew up in Taiwan, and I watched baseball growing up. And when the Cubs finally won the championship, I just couldn't resist naming a project after the Cubs. But again, so today, as Pepe mentioned as well, my main research interest is on the diffuse gas content around galaxies that many of you are familiar with. I hope to surprise you or impress upon you just how much more material there is out of the luminous regions that we have, you have seen in space or ground-based images, and also just with your naked eye here in the dark sky. And in fact, there's a lot of physics ongoing that helps regulate the growth and the evolution of the galaxies like our own. And that's very much of what the CGM workshop is focusing on this week. So since I'm going to focus on gaseous halo and also with a special focus on turbulent energy cascade in the physics context, on the right, you can see that this is an image of what you might see with very clear sky and maybe somewhat powerful telescope. It shows three primary galaxies among a dark background. And these are precisely the stellar light that you are familiar with in many beautiful images. That's not what all there is. And my talk is going to focus on kind of diffuse gas content that connects. Here you go. So this is the same field, now with the diffuse gas content overlaid on top of optical image. You can see through the combination of 21 centimeter, it's a radio observation, and also many multi-wavelength data, radio all the way up to high-energy X-ray. It helps review the complex physical processes that draw gas, the gaseous material coming into the otherwise isolated-looking galaxies that you see just with naked eye or optical telescope. And it's the kind of multi-phase, multi-scale phenomena that we are trying to understand. So just for those who, just so you can appreciate the kind of multi-scale process we are talking about here, the typical galaxy disk, like our Milky Way, is about 20 kpc across. This is, the size unit that astronomers are familiar with. This is kiloparsecs, where each parsec is about 3 light years. So what you're seeing here, the disk is about 65,000 light years across. So we started out with this large-scale, galactic-scale structure, zooming in on small disks, disk scale here, now on scales of 2 kiloparsecs. And further zooming in on yet another orders of magnitude in on really zooming on parsec scale. All these, the phenomena appear to be connected with each other. How do we characterize these? It's very much the question we're trying to understand. Just quick outline. There's a bit of lag between the switch. Just need you to bear with me. So a quick background, just so we can get on the same page about what the driving questions are in the context of understanding the cosmic ecosystem. It includes starting from the smallest planets, stars, to galaxies, galaxy clusters, to the entire universe. And moving on to talk about a couple specific techniques we use to study this multi-scale, multi-phase phenomenon, starting with absorption-line approach it's like a backlight through negative image process to map out the diffuse gas structure along each single slide line. To now we are entering into very exciting 2D spatially resolved emission line mapping that really facilitated the central topic I'm going to talk about today, which is the turbulent velocity cascade that connects energy from different scales together to shed light on how galaxy growth is regulated by star formation or supermassive black hole activities to the giant, vast cosmos. I hope I will have time to talk a bit about physics, what we have learned from this. So very quickly, again, just to motivate, at this day and age, I don't think I can get away the talk without showing the beautiful image coming out of the James Webb Space Telescope. It really brings distant cosmos into very sharp focus. And this is a cluster, strong lensing cluster field. I'm not going to talk about strong lensing today, but happy to talk offline. But you can see that there's a lot, so most of the galaxies, I should say, came out of beyond when the universe was only a couple billion years old. We are now at 13.5 billion years. It's really just how powerful. I just want you to mentally adjust to the fact that we are looking into the initial 2 to 3 billion years of the universe, this sharp image. And you can already see some really well-formed galaxy structure, very similar to the first image I showed earlier. And I need to adjust the time lag. If you look at zooming in on individual systems, what you see here is I marked here to the right with increasing stellar mass. Total mass that's already locked in stars in individual galaxies. Going down is going back in time to earlier times. And hopefully it's directly obvious to appreciate that there's a well-formed disk structure on the upper right corner as a high mass and nearby, closer to the local present day. And as you go back in time, the structure starts to change. We start to lose this regular structure. And this is despite the fact that many galaxies appear to be different. Every single galaxy, all the galaxies coming in all size, shape, and color. Here is a general global trend that can simply be characterized by a uniform relation. So it just tells us that despite many chaotic physical processes that can be in play, there's a general guiding principle that forms a simple, coherent, the kind of global relation. That's the kind of, so one example is basically if you look at the global star formation rate density as a function of time, you can see this general rise in time. So astronomers also use redshift to measure the distance and also time because it takes time to travel. And if you focus on the top axis, it shows the look back time. Again, so local is here, and going back to the beginning is about 13 billion years. And up to the first 3 billion years, formation was happening in full force. It goes up, but then it starts to decline, also really rapidly. What is driving that? That's connection to the kind of drastic change in the appearance of the galaxy is very much what we're trying to understand. In addition to simple relation, between different physical quantities that we have known. I'm not gonna say much about that. Just take my words that despite the chaotic, appearance in galaxy morphology, there appears to be some ordered relation that governs the galaxy formation and evolution. So in order to understand, get physical understanding of what the processes are actually doing this work, it's important to step back and look at the global environment. So we start with, in astrophysics, irrespective of what dark matter is, we actually understand large-scale structure formation through the dark matter clustering very well. All simulations, basically, this is one snapshot that I borrowed from the illustrative simulation. Again, so box size is about 50 megaparsecs. Again, 1 parsec is 3 light years. I just want to, later you're going to see just how big the volume is. If you look at the dark matter distribution, you see a lot of structure here. There's no surprise here. But if you look at where galaxies are in the same volume coming out of this simulation, this is where you would expect to see where stars lie. So all the pretty galaxy images really occupy the peak of dark matter density fluctuation and tiny little volume. Galaxies form in the deep potential well set by the dark matter. So where is the most of the baryon that we know out of the Big Bang nucleosynthesis? And you look at the same simulation, it tells you that more than 90% of the baryon lies outside of the stellar body of galaxy. It really drives home, at least to me, the importance of studying this diffuse gas matter. Diffuse matter, without understanding what's going on from this megaparsec volume to the tiny parsecs where star formation happens, is critical but very challenging. And this is the kind of circumgalactic medium that you heard about. So once we zoom in, this is the latest simulation rendition coming out of this review article written by Andre, who's here, and also Peng O, somewhere in the audience. Yeah, both of them. That shows the complex. I hope you can appreciate with a rotating disk at the center of the image, driving potentially large-scale outflows, hitting the surrounding intergalactic medium. If you zoom in, you can see this multi-scale, very complex multi-scale structure. And as you continue to improve on the resolution, you see a lot of phenomenon going on. So I hope one thing, going back to the theme of this talk, is turbulence. You can see the very turbulent material coming out of this extremely high resolution simulation. So as it turns out, in astrophysics, similar to physics, we do decadal survey led by the National Academy of Sciences. In the after 2020, within the cosmic ecosystem, the priority area, in fact, is to understand the hidden driver of galaxy growth through studies of the circumgalactic gas. So now going back to the simulation image, just want to highlight the challenge not just in simulations, to resolve, to try to characterize fields that spread over 6, 8 orders of magnitude. Observationally, this is also incredibly challenging to find the right probe. So now here's hopefully a good illustration to show you just what we are dealing with. Out of the 50 megaparsecs box, if you just focus on the tiny little square in the middle, this is what you would expect for the local group galaxy. In the local group, there are 2 big galaxies. There's ourselves, the Milky Way, and the nearby neighbor, the Andromeda galaxies, surrounded by a large number of satellites. And this is about 1 megaparsec in size. Again, we're talking about order of magnitude. So if I zoom in on individual galaxies, you can see the scale, at how small that is out of this cosmological volume. And I continue to zoom in on individual clouds. You can see that on parsec scale, we start to see individual structure, not quite clouds, but over density that's falling into the main disk. And there are certainly much smaller structures there. So what are they doing in terms of regulating and feeding the growth of galaxies? How do we study them across this vast dynamic range? So what comes with the vast scale, you should only expect a vast dynamic range in the temperature and density space as well. Just by looking at, again, trying to learn from what simulations can tell us, the expectation out of this circumgalactic gas, basically this is the galactic atmosphere, the density range goes from anywhere beyond 1 particle per cubic centimeters down to 10 to the minus, below 10 to the minus 6. I don't know if there's any experimentalist in this room. This is perfect volume of the experimentalist. Probably nobody can reach this on Earth. Yeah, this is the material we are studying. The temperature ranging from 1,000 Kelvin all the way up to 100 million degrees. It's a gigantic phase space that contains 90% of the baryons, and minimum of 90% of the baryons, simply because of the volume we are talking about. Despite the low density, there's all the mass. Basically, again, order of magnitude speaking, this is really what we need to focus on in order to understand a lumpy universe and how galaxies we see come and evolve. So just as an illustration, going back to the outline, that was my intro for the background science case. And now it's just moving on to introducing one of the techniques we use, which is the absorption spectroscopy. So this is a different, a separate cosmological simulation box. I didn't mark so this is about 10 megaparsecs on the side. But you can see this kind of cosmic web filamentary structure that is expected, tracing the underlying dark matter distribution. So the idea that has been going on, so this has been going on since as early as the 60s, when the first high redshift quasars, were found in the middle 60s. So these are supermassive black hole powered accretion disk. It's luminous, serving as a background light beacon shining through space. Imagine if the photons intercepting any of the filaments is going to interact. There's a radiative transfer. You can see that a photon coming in, hitting a hydrogen particle, it's going to excite the electron. And the end result is to leave the imprint, a deficit, attenuation of the background flux. And that's what we consider a line. And this is typically because hydrogen is the most abundant element in the universe. This is a very typical Lama alpha photon, transition from the ground state to the first excited state. And likewise, we know the electrons will come down actually in no time. So the complementary process is emission. So as the background light beacon moves through space, it will form absorption features as every single filamentary structure that they hit. The electrons will come down, re-emitted into the surrounding medium creating emission signal. So the complementary approach is to try to detect an emission, just like an image. But that's a very difficult thing to do because, as you can imagine, it's a two-body interaction. It's a very nonlinear process. So even if we can detect something, this is very much focusing on the high-density peak. Complementary to absorption probe is really, this integrated interactions. So it gives you the total column across, each structure here. So just to share a very quick movie to give you a sense. So, and because of the, with the help of Hubble flow, basically the universe is expanding. And because of that, any source every source is moving away from us. And the kind of redshift help us to help the feature to be resolved. To be separated as a function of distance. So this is so-called lemma alpha force as the source moving further away from us. The absorption feature will appear at different wavelengths. This is the so-called lemma alpha forest. It tells us that the space is not empty, and they confirm that 90%, more than 90% of the material is in the intergalactic space outside of the optical disk that you see in deep imaging data. So the good thing about this is it's not just hydrogen there is in the universe. There's also heavy elements made out of nucleosynthesis that happens in the center of a star. And through stellar evolution, these elements will be ejected back into space and pollute this otherwise pristine volume. And so if you look at the typical high redshift quasar, the backbone light beacon, here are broad emission. This is a spectrum now of this light source. And I must clarify that astronomers use angstrom as the wavelength unit. This 10 angstrom corresponds to 1 nanometers. So hopefully you can. So this is 500 nanometer to 800 nanometer at the bottom. This is going into the ultraviolet now from 350 nanometers up to about 500 nanometers. A typical quasar redshift 2-ish. So this is when the universe was about 3 billion years old. Typical redshift quasar spectrum looks like this, broad line, but with this absorption, noisy feature that's the lemma alpha forest from the movie you saw earlier. For a large fraction of these lemma hydrogen lines, there comes with associated absorption features that's produced by the heavy ions that are in the same gaseous structure. And they come in different ionization states. The good thing is very oftentimes they come in pair. So it's purely just atomic physics, depending on the electron structure, and that gives us a very clear sort of fingerprint of what the features, the origin of these lines are. These include some relatively low energy ions, the singly ionized magnesium, intermediate carbon to highly ionized O6, that's 5 times ionized. And through this, in fact, there's more than just these species. If I go back to the density and temperature space diagram, you can see that within these different part of the space, phase space, these different ions gives us a probe to study the particular gas content, particular phase. So like down here is a cooler 10 to the 4 Kelvin gas, relatively high density. You can study effectively with these singly ionized species. Intermediate state, as the number increases, you increase the temperature, the energy regime. The highest species that we are typically studying, like oxygen 6 and neon 8, will be studying into the X-ray plasma regime, still slightly cooler. Just want you to remember that these are the lines that I will be referring to. They are more than just alphabet soup. They actually translate. I want you to remember that for low ions, ionized species, we're talking about insert gas, and the highly ionized ions, we're looking into warm, low density phase. So moving on, I want to introduce this CUBS, the famous CUBS program that we started many years ago, in fact, in 2017. And this is the COPS player. I just want to highlight many of us are actually here or will be here for the CGM workshop. I want to especially call out to Gwen Rudy, who's one of the co-PI on this project. You can also see Carl Andre, Zhijie Xu in the audience. I encourage you, if you have any, so Aaron is here as well. She's online. So if you see these people around on campus, feel free to talk to them about what COPS is about. What is COPS about? This is really a large Hubble Space Telescope program designed to use 15 different light beacons in random location to probe the diffuse gas content along the line of sight in 15 different random fields. The idea is to use the absorption spectroscopy I mentioned earlier to study how diffuse gas content is coupled with galaxies along common sideline, connecting the two thinly disjoint entities to understand the galaxy formation and evolution, but also to track chemical enrichment. Remember, the heavy elements are really produced inside stars. How do they get dispersed into the cosmological scale? Still very much a puzzle. Now we have a lot of state-of-the-art numerical simulations that we can compare with, really test comparing observations and simulations theory to test our understanding of physics. And the second phase of the project, which was only approved a couple years ago, we coined that as contact, expand the access to the diffuse gas content. What's unique about this program is, in addition to the absorption spectroscopy, we also have very deep galaxy survey effort that's really led by Gwen at Carnegie with enormous amount of telescope investment. How we can actually survey all the faint galaxies along all 15 fields. The idea is, so just to give you an example, the absorption spectroscopy gives us a very sensitive 1D probe down the sideline. But it's very much the universe is a 3D structure, especially when it comes to coupling the gas content with stars. We need to know what kind of galaxies are around each absorber. And this is to show you that at the top, you can see the redshift distribution. Apologies for the resolution. We just want to quickly illustrate that the redshift histogram that goes back, again, redshift is a measure of cosmic time, lag time, and this distance. You can see that the galaxy distribution is not uniform. You see a lot of peaks here. It comes in a lumpy structure. Now, the question is really, if we see a cluster of galaxy at some redshift, what is the gas? Where is the gas? What kind of gaseous structure we are seeing? But here, just to show one example at this particular absorber at 0.16, these are the red dots are the kind of galaxies we have identified out to megaparsecs. Relatively loose structure. But if you go to the next one, you can also see that there's additional little line absorbers that I mentioned earlier. Again, there's sort of quite random, but not quite random. You can see there's a string kind of connecting dots across the field. This is one that corresponds to this peak here. Naturally, you can see, overdent structure at the same redshift where we find an absorber. So the idea is really to combine absorption spectroscopy with galaxy surveys, build up this 3D image of the cosmic structure that includes hopefully all the mass that we know exists. So what can we learn from absorption spectroscopy, especially the very high resolution? Through a line, we can resolve all the particles. They are not static in space. They are all moving around. And that's in addition to the Hubble flow as they move away from us. But through identifying the line profile, we can try to associate different species, try to build physical connection between different species. And this is an example of an absorption system. You can see that instead of one dip, there's actually two dips that we see in hydrogen. This is H1 gamma beta absorption. This is coming from the ground state to the second excited state. And also higher state here. On two of the hydrogen transitions, we see double components. And so it tells us that along this particular sideline, this particular system, there are at least 2 overdense regions that we intercept. And not just that, the 2 regions appear to have different density scale, because they show different corresponding ion structure. The orange component I highlighted here, we don't see low ions, thinly ionized species, but we see very strong absorption coming out of this O6 doublet. Remember, the number 6, this is the highly ionized species that happens at high temperature at about 1,000,000 degrees Kelvin at low density. So when you look at, so this revealed through the resolved spectra, we reveal the low density warm ionized gas in this particular system. In contrast, there's a second component here with stronger hydrogen absorption. We see really strong associated low ions, but no corresponding high ions. So just again, so this is the 1D map of the multi-phase structure that we can study revealed with the absorption spectroscopy that is revealed based on kinematically distinct profiles. But they are complicated. They are more complicated situation where even the kinematics cannot help us. We only see basically one single dip all across the low to high ions here. What do we do there? Well, at least physics is our friend. We know that just based on ionization mechanism, there's no single density phase, no ionization mechanism we can imagine or understand that will produce all these vastly different ions in one shot. Because as we increase the ionization potential to the right at the bottom panel, for a single density phase, we can match all the low ionization species. When we move to higher ionization states, we start to fall short, the prediction, fall short in terms of matching the data. This is when we know that even when you see everything, all the particles moving at the same speed with similar width, there's actually multi-phase here. There's at least minimum of 2 density phases. So with this, we can reconstruct this gaseous atmosphere that we otherwise couldn't see, because this is all very low density gas. One sideline at a time to build up the density profile. So what you see here is every vertical dotted line shows one system spectrally resolved into multiple clumps, multiple overdensity structure. It shows that the halo really is complex and dynamic. We can actually compare the expected pressure. We know the density now, we also actually know the temperature. We can work out the pressure, compare that with studies from other wavelengths, examine whether this is in pressure equilibrium, kind of weather systems there is in every galactic halo. This is the image we constructed for distant galaxies. Even though we cannot see it in direct light, through absorption-line measure, we are really constructing the galaxy atmosphere to show that from beyond the central disk, there are multiple clouds that are interacting with each other, either shared or disjoint spatial distribution. And through this, we can also infer the size of these typical structure. It comes out to be with the median size of 100 parsec. Again, so this is larger than the solar system or than the nearby H2 region, even though it's not as big as a galaxy. It's about the thickness of a disk. In addition to the density structure, we can go back and take a deeper look at the kinematic structure. Again, going back to basic physics, when the gaseous structure interact with the photon, it carries the kinematic information when during the radiation interaction. So the line width we observed carries at least 2 distinct contributions. It's a thermal motion that broadens the line that we would expect to see, but there's also non-thermal. Simplest case would be Hubble flow that will contribute to the line width, but in the smaller scale, turbulent motion. It's really central to the topic here. Will also contribute to the line broadening. Differences, there is a systemic motion, or this is thermal, that depends on the mass of the particle. So with this, why do we care about this? If we can decompose the temperature flow broadening from non-thermal broadening, we can estimate the thermodynamics within the cloud. And just happens that the thermal energy fraction is directly related to the Mach number within the cloud. And when we do that, we look at the galactic environment, the nature of the galaxy. We found that, primarily speaking, most of the clouds are really driven by thermal motion, meaning the motion of the particles is largely subsonic, with a slight hint of, when we focus on massive evolved systems, there's a slight enhancement in potential supersonic motion within these clouds. And combining the ionization analysis that I mentioned earlier with kind of kinematic analysis, we can look at just simply the velocity size relation. So what we find is larger clumps, the non-thermal motion appears to be also more active, also stronger. There's really no reason for that. So as we go down to smaller and smaller clumps, we find that the non-thermal motion is also more quiescent. So we are able now to go down to about parsecs with this absorption-line technique. This is really a first that we're doing. I'm going to come back to this just to highlight why this is so special. So bear with me. So going back to the theme of the talk, basically, why do we care about turbulence? So just highlighted a few examples here why turbulence is important in the whole discussion of the evolution of the gaseous content and how that regulates the galaxy. It provides additional pressure support, additional heating, and also provides triggering additional condensation through the density fluctuation. Not to mention the Bell transport. In my mind, the most illuminating property is providing us a way, the insight into how energy on different scales coupled, which is really critical when it comes to understanding how starburst, supermassive black holes on tiny little scale inside the galaxy can influence the large-scale halo environment. And I think turbulent energy cascade is very much the key holder in that question. Going back to this figure I just mentioned, velocity size relation, especially the velocity here is about turbulent, not thermal motion. It's actually very consistent with the kind of turbulent spectrum expected for isotropic and incompressible gas that people have been studying in fluid dynamics. The Kolmogorov relation predicts that if the fluid is incompressible and homogeneous, the turbulent velocity field is subsonic, and the energy transfer from one scale to the next is constant. So the energy can go from large scale and cascade down, dissipate into the gas, heating up the gas with this turbulent spectrum. And based on what we observed, it's actually matching Kolmogorov very nicely to within the uncertainties. This to me is really intriguing. So now that's the line of sight measurement. That can so certainly one can argue that there are other potential contribution to the kind of non-thermal broadening that we see in absorption-line measurement. But now moving forward with the large-scale emission line maps that I mentioned at the beginning, we can actually try to measure the turbulence spectrum based on observed decorrelation across different sight lines. This is what's called the velocity structure function. It measures the velocity difference within one nebula as a function of separation.
So this is really measuring how fast it's become decorrelated, stirred up. And there's a very simple, very nice self-similar expectation coming out of the Kolmogorov relation again. For different moments, the velocity difference, as in the parallel P here, there's a very simple expectation that the older the moments of the velocity difference scales with P2 divided by 3, third power. So this gives us a very nice empirical measure. We can actually measure it without much trouble. So we start with the second order, simply because it directly translates to kinetic energy. And when you start with that, you can actually work out the energy transfer rate at any particular scale. If it's Kolmogorov, it really doesn't matter which scale you choose. And what we did, we started with the luminous quasar nebulae. This is extended, line emitting gas that we detected at around the redshift of the quasar, supermassive black hole at redshift 1-ish. That's about 8 billion years ago. This is really large scale. You have to take my words for it. 100 kpc across. That's 5 times size of the Milky Way disk. We measure, I should say this is led by the grad student Mandy Chen, who's now moving on to Princeton postdoc fellowship at Carnegie and Caltech. So Mandy measured the velocity structure function multiple moments and discovered this really beautiful Kolmogorov relation slope out of this nebula. And not to mention, we actually, when we go out to 40 kpc, we start to see the flattening. Typically in experiment, this will be indicating energy injection scale. We might be actually witnessing how the energy is being dumped into the galactic atmosphere. Then you can see that, obviously it should be clear to you that this is not a straight line. The only reason this is bending down is because of the smoothing due to the atmosphere seeing turbulence in our own atmosphere will also smooth things up. So we fold that into our forward modeling. That's what we found. And so what this is telling us is that the turbulent velocity spectrum, even around these massive, supermassive monster black holes, is Kolmogorov. This is very surprising, but you can see that the scale here, the energy scale here, this is delta V square. You can work out the actual velocity dispersion is on the order of 200 ampere per second. But the typical temperature, this should be supersonic. So what is going on? There's a question pending. We continue to move on to looking at different nebulae, including, so the first example was radio loud. So this is considered to have push out the radio lobe, produce the radio signal. This is an example around radio quiet quasar, where we also determine a very nice Kolmogorov slope. And now we have also analyzed a non-quasar host halo, meaning there's no supermassive black hole in this particular system. This is a system I found in 2019 where we detect extended emission, very typical nebula lines at redshift 0.3. And now undergrad student has taken up the task of measuring the velocity structure function, also discover a very nice Kolmogorov. So, but as you can see that our measurement here really is fundamentally limited. So the ideal case scenario is to really detect the dissipation scale. It's really small. But even without detecting the dissipation scale, we still would like to see to push down to scales that's comparable to star-forming region. But to do that, we resorted back to James Webb Space Telescope again, going above the atmosphere. This is the one system we study, and that actually shows very complex environment, starting from quasar outflows, the giant jets that's being driven out, to just tidally stripped material coming out of satellite galaxy. And this is the flux map and velocity map that Mandy had measured. And by separating, so there's also a second source that we study that's at slightly higher redshift. In this case, you can also see the instrument availability. We can resolve the nebula, detect the nebulae out to about 20 kpc. in radius. So by this time, you can guess what I'm going to tell you. We measure the velocity structure function again down to 1 kpc range. What we found is within 4 to 5 kpc is actually consistent with Kolmogorov. But that's not the interesting thing I find about these couple sources. The most interesting thing is this very clear flattening that happened in the middle. I mean, that's closer than the size of the nebulae. Before, I didn't say we see this potential drop. The velocity structure function that's 50 kpc is about the size of the nebulae, so I didn't quite trust it. But here, the size of the nebulae goes out to 10 kpc, and the velocity structure function flattens before that, way before that. Hey, this is very clear indication that this is the energy injection scale we are seeing now. So if you're wondering about this gradient removed or direct measurements, ask me the question later, but I'm just going to ask you to focus on this gradient removed panel. For both systems, there are 2 quasars, remember? One quasar has the tidal gas, tidal stream off to the corner. All 3 entities follow Kolmogorov on small scales. But the quasar systemic gas consistently showing higher power, higher kinetic energy power. When you focus on the tidal gas further away, it's almost an order of magnitude weaker, but still it follows a very nice law. So I'm running out of time, so I'm just gonna quickly go over what we think is driving the turbulence that we are seeing. On large scale, we can turn the velocity, the power back to, in addition to the energy transfer rate, we can also work out the eddy turnover time. How long it takes for the energy to dissipate. And in the giant nebula case, the time scale works out to be of over 200 million years. I think many of you know that quasar lifetime, the monsters cannot live forever. In fact, only last on the order of 1, 10, maybe 100 million years. That's pushing it. And this requires to sustain the turbulence. The source has to be lasting longer than 200 million years. So it doesn't look like the quasar, the monster in the center that's driving the turbulence. It looks instead, because they are also, when we do the galaxy survey, we found a large number of satellites. So this judging learned formed by the Milky Way halo, our own home. There are hundreds of satellites found. They are all interacting with each other. We see stellar streams everywhere. But it really looks like it's the satellite interaction that's dumping the energy to drive the turbulence. That's not the case with the high redshift quasar that we studied. Remember, this is on smaller scale of order 5 kpc, and the eddy turnover time is an order of magnitude lower as well, 20 million years. Comparable to the quasar lifetime, so it could work. In addition, there's also a starburst that happens along with the monster. So it really looks like that at least in the host environment of these supermassive black holes, could be the quasar that's driving the outflows. But there's also indication that there's the interaction between outflows and the accreted tidal stream. It's also collectively stirring things up. So we are actually seeing this for the first time. It has tremendous implication for the AGN, the quasar regulated feedback in galaxy growth. So I'm just gonna put up the summary. Just very quickly to remind you that astronomers are very creative. Even though we only have one laboratory, which we have no control of, we have our own tools, help with many creative instrument builders that allows us to combine absorption spectroscopy and emission measure to start probing, connect dots. And now, the one thing I focus on today is the turbulent energy cascade in an environment full of matter, but unseen of our naked eyes. And we're making tremendous, just to show how the eddy turnover time from large go down to small clumps. And also the difference in the turbulent energy. I'll stop here.
Question time. And I'm told that non-astrophysicists should ask questions first.
Great talk. Has the turbulent cascade has also been seen in the interstellar medium as well?
Right.
Does it have a similar slope?
Yes. No. Yes and no. Depends on where you look. So. Oh, right. So the question is, has the turbulent cascade been seen in interstellar space? And the answer is yes and no. And what kind of slope it showed? So it depends on where you look. Oftentimes people see slightly steeper slope that indicates supersonic motion. And in fact, this pale brown band here indicates measurements from interstellar molecular gas. And people are finding the slope is actually, deeper than what we expect. But that's also consistent with the supersonic motion people see.
Thank you. So I'm wondering, because some people would argue that quasars, and in particular red quasars, are driven by recent major galaxy mergers, right? And so how can you disentangle the sort of direct quasar feedback and driving turbulence compared to recent galaxy merger activity?
The question is, people have found that, especially for red quasars, it's triggered by major mergers. So how can we tell the difference between quasar outflows or merging events? So this is what I'm trying to explain using this example here. This red stream is tidal stream. We can actually see stellar counterpart in space telescope images. And this is a red quasar. It's very extreme. The tidal stream we can identify based on very distinct kinematic properties. They showed up at very different velocity, very narrow in line width. Unlike the systemic gas is broader, it's at a different velocity. So we measure the structure function separate. So this is probably not the right, but just want to remind you that for the quasar host environment, we see a very clear flattening at 4 kpc, and also much higher power. In the tidal gas, it just kind of continues. It's a shallower term. It's not very distinct, but it's also lower powered. So it's both the slope, the flattening, and the power that can tell us how far out the quasar outflow is influencing the gas. So this is why, I know that a lot of observables have ambiguities, but I think here it's quite clear that at least in terms of driving turbulence, the red quasar outflows is not doing too much work beyond the 6-8 kpc range.
You mentioned that the energy cascade behaves as incompressible. Is there any reason why this very dilute gas behaves as incompressible liquid?
That's my puzzle. We know the gas. We know. Oh, right. The question is, the Kolmogorov law applies to incompressible fluid. And is there a reason to think that the tenuous gas here is incompressible? So I'm very puzzled by the finding here, because we know, even though we know roughly speaking, they might be in pressure equilibrium with a hot medium, but there are many different processes that can destroy or compress the gaseous cloud. And yet we see this, very nice, Kolmogorov relation. So that's very much an open question.
Total turbulent velocity is very that to the very real velocity of the halos, the quasars.
So it depends on which experiment you're talking about. Along the line of sight, the dispersion is very low. So, the scale is on the order of 10, 20 kilometers per second. Across line of sight is very high. It's 200. So the thinking, the idea is if it's turbulence within the cold gas, it will be supersonic. It wouldn't show the shallow slope. It should be steeper. So my interpretation is that the cool gas that we see, the nebula we see, is serving as a tracer particle that's being pushed around by the potential hot medium. So that's one thing I forgot to mention. Thank you for asking. That's an indirect evidence for the presence of hot medium that we cannot see. And that's also, that helps us understand subsonic behavior.
Any more questions? Remark? Well, just to say, I think in the future, if we can get a new flagship X-ray mission, something very large, and we take pictures of the sky in that energy band, and if I'm right, well, we should see all.
You are absolutely correct. Helping the best that I can to advise NASA that we need the X-ray window, need multi-phase. We cannot just look at one frequency and try to understand such a complex system. We need really multi-wavelength probes in order to learn all the physics there might be that's driving all these different processes.
All right, thank you.